Okay. So we can start, guys. This is our last meeting for this year. It has been a big journey so far. And today we are concluding with Gordon Lassen, who is a PhD student of the National IA program. He's co-supervised by Xerici and by Guardo. And his research project is along responsible AI and deep learning. And he's going to give us a hint of his current work in progress. So thank you, Nicola, for joining us. Thank you. And the floor is yours.
Thank you, Emanuele. Thank you, Nicola. Thank you for having me here. It's a pleasure to be the last speaker of this journal. And my speech will be about this properties in Generative Face Anonymization presentation. It is my work, which I presented at GitHub 2021 last month. And in the end, I will give you some points from my current research. The speech will be divided into this first section. I will talk about the reasons why we need privacy conserved machine learning, with some things about the current legislation in the European framework. Then I will give you a very brief recap of what generative models are, which is the state of the art in terms of the face anonymization. Then I will present the work itself, and at the end I will talk about my current research and my research directions. So, why do we need privacy conserved machine learning? Let me start with the legal landscape of AI in Europe at the moment. As you for sure know, the most important law that we have at the moment is the General Data Regulation, the GDPR from 2016, which regulates the privacy of security of personal data on the European territory, and also worldwide if the company works with European users. It provides some mandatory rules for the organization on how to collect, store, process, and delete data. And one of the most important points is that the collection of the data must have a defined purpose, and they cannot be collected without one of those. This is a general law which applies to every type of data and does not address directly artificial intelligence. And for this, last year, the European Commission approved first draft of the Artificial Intelligence Act, which is a new proposal for the regulation of artificial intelligence, which poses some limits to the usage of artificial intelligence and the use of data, and it will cover any type of AI system, starting from statistical methods to any machine learning or deep learning approaches. The most important part of this new regulation is that any AI system will be divided into 4 categories of risks, starting from the minimal risk, which do not have any particular regulation to address, while going up until the unacceptable risk, whose applications are forbidden completely on the European territory. And part of these are, for example, the social scoring and the use of real-time biometrics to identify people in public spaces. But a question may arise: can we use biometric data for law enforcement? Actually, the GDPR states some exceptions to the complete ban of the use of biometric data. In particular, when the public interest is involved in this type of applications. Live identification is not possible apart from some specific investigations, some particular crimes like terrorism or human trafficking and so on. But the AI Act, in the Artificial Intelligence Act, this is still an ongoing discussion. Some members want more exceptions to the use of identification, while some others don't. But why am I talking about this? Because last year, during my internship, during my master, I worked in the film healthcare, and I collaborated on 2 European projects. Marvel, which two different projects, but their goal is common, and they aim at using the data coming from our smart cities to improve the safety of our cities by analyzing videos, audio, and using them to prevent unfortunate events this way. So what we wanted to progress is the anonymization without compromising the data. So the goal is to anonymize video streams without preventing the analyzability of other systems, for example, emotion recognition or anomaly detection. We wanted, therefore, to remove any personal information from the images of recorded cameras, but preserving this possibility to analyze them. Classical techniques like blurring and pixelation are very effective for removing personal information, but they destroy the information about the activity or the emotion a person is experiencing. And therefore, we want a non-degradative way to solve this problem, and this is where deep learning comes into the picture. We developed a face swapping algorithm to anonymize without compromising. You may argue that anonymizing the face is not enough to anonymize the person, and this is true because there are some words stating that also clothing is important to recognize a person. Also, how we hold the gate is an important trait. This is for work. Before going further, let me clarify some terms I will use in the presentation. Landmarks will refer to efficient landmarks, which represent salient regions of a face and which can represent the expression and the pose a person is having. And depending on the type of deep learning them, we have different numbers of it. For let's say, landmarks are type. While face swap refers to the transfer of identity of a face from one condition image to a certain image while preserving both expressions. Okay. Before going into the model itself, let me give you a very quick recap of how generative models works, and in particular generative face network, which is what I used in this project. The goal of this generative model is to map from a simple known distribution into a more complex real distribution. The goal to approximate as well as possible the original distribution of data. This is a difficult task because it is very sensitive to the hyperparameter choice on the similarity metric between the generated space and the original one, and the latent space itself. During the years of deep learning, we have had a lot of different models. And this is a non-exhaustive taxonomy of them. I will talk mainly about generative adversarial networks, and by the end of the presentation, I will give you a brief introduction of these new diffusion models, which are a special category of operational autoencoders, which in the last 2 years have been really popular because of a set of desirable properties that we will see later. Generative adversarial networks are types of generative models training data space with an implicit density of the data space, where the similarity between the generated data space and the original space is performed through a second network called the discriminator. And the goal is to let these two networks play while one tries to fool the other, and to reach in the end an equilibrium where the generator is able to fool the discriminator into thinking that the samples generated are real. There are a lot of problems in training GANs, gradients which vanishes, multiple labs is one of the most common issue, where the generated mentioning, the generator is small, non-big distribution, usually Gaussian, and there's a mapping from this to the data space, and the discriminator as the objective to tell if the input is true or fake. And the goal is to find an equilibrium between these two. Here I have nice noise going through the generator, generating samples, and the discriminator is as if we are taking samples to generate equivalents of the generator. These are some of the results of the first generative network by Fellow. The network was a simple network at that time, so the results are not very encouraging. But since then, we have had the evolution of our networks, we have transformers. So the generation reached a point where we can generate high fidelity faces, work between them, play in the latent space, and have this astounding results. What you can see here on the right is the latest model by NVIDIA style GAN-3, and the results are impressive. Second point is that the generated images still have some problems, in particular for the face generation. There is the possibility to distinguish if an image is fake or not, given some traits of the face, in particular the eyes. There are some studies about the side on images, and you can see that the eyes are always in a fixed position with a fixed shape. This could give a hint if the image is generated or not. One which is more interesting is the heartbeat, because from a picture of a person we can extract, we can approximate the heartbeat, and the faces generated by neural networks do not have this capability. So the network the heartbeat will not work on fake images. Surprised me a lot. Lastly, what is the state of the art about face swapping? The network we named Berwick is this GAN because it was the only one following RC setting privacy serving network, but it traded a lot between face fidelity and anonymization performances, and we will see the results. While in a more general framework of face swapping, the results are more are better, and the field is saturating all the results. Sorry. Okay, now that we have all the pieces, I can talk about my paper project. Graph-based anonymization.
So my project was this one, where the framework is the one that you can see in the picture. We have a network takes as input a condition face, which is the non-sensitive identity. We want to substitute on a source image with the facial area removed, so to avoid the leakage of personal information throughout the network. And these two images are concatenated and fed into an appearance encoder, which extracts some features about these two faces. And on the other end, we have another branch as input, which takes as input the landmarks of both the condition face and the source face, so that we can learn a mapping between the two to transfer the face from one to another. I will talk briefly about the landmark attention model, but after that, the landmarks are encoded with this shape encoder to reduce the spatial resolution. And then after this, we build a bipartite graph between the two sets of landmarks. And we reason on top of this while incorporating the information coming from the appearance branch in order to merge the appearance information. The final generated image is fed through two different discriminators, one to ensure that the pose is correct, which is the landmark discriminator, while the other, the appearance discriminator, maintains some high-level information such as the skin color, which we want to preserve from the source, and the background. So the landmark attention model that was briefly mentioned is a way to reduce the number of landmarks needed to the network to operate, because from the literature, we know that not all the landmarks are needed to preserve the pose, but instead of selecting them manually, as done in previous work, so we'll have the network weight the importance through this landmark attention model, which effectively is just a channel attention which reduces the number of input channels. While the graph is built on top of these filtered landmarks, and while after projecting it to the feature space, we reverse after reasoning on top of this, because it's a convolutional graph neural network. We reproject it back to the coordinate space, and we incorporate this with information coming from the appearance branch. Lastly, the two discriminators, as I was mentioning, we have an appearance discriminator, which helps to transfer the context attributes, such as the skin tone and the background. And the landmark discriminator had the goal to preserve the pose. Okay, how we evaluated our method. We followed the same setting as our competitor, our GAN, and we used two publicly available datasets, this Salivate and Lablet Faces in the Wild, which are two large-scale faces dataset, and we extracted the landmarks using the standard dlib. As metrics for evaluation, we use the Fréchet inception distance to assess the quality of the generated image. For the post-preservation, we adopted an L2 distance between the generated landmarks and the ground truth landmarks of the source image. We wanted the generated image to be recognized as faces, so we used the two detectors to understand if the generated image corresponds to a face. And for the re-identification, which is the goal of the anonymization, we used a pre-trained network for face recognition, and we reported the percentage of faces which get mapped to the original identity. Some qualitative results, we can see that the generated faces by our AnonyGAN have a higher quality with respect to our competitor. The attributes of the condition are better transferred to the final output, while having also a better preservation of the pose. From a quantitative point of view, we can see that, of course, the best anonymization performance is achieved by the classical techniques, such as blurring and pixelation, but because they destroy the information about the face. While on the other fields, we can see that we achieve the best looking images, the FID, the lower the better. All our faces are recognized as faces, and the pose is the best preserved. We have a minor trade-off between the face quality and the re-identification performances. But our ablation study proved the effectiveness of all our contribution, both the landmark attention and the additional loss for matching the context. They prove significantly for the final results. And this is more or less the summary of the paper that got accepted at ESUP. After that, we tried to do some more work on top of this, but what didn't work, which are also the reasons why I'm changing topic right now, is because the method, as it was, it requires some precise localization of the landmarks, which is actually impossible in some live settings, such as CCTV cameras. And we try to have an implicit representation learned by the network, but it didn't work. We didn't have any explicit constraint on the time dimension, so it didn't work out of the box on videos, although other methods for face swapping claim they can work on videos out of the box. Then lastly, what we tried to do was to use some transformer into the generation, hoping that the global the global attention could better generate the faces, having some more coherence throughout the image, but in the end, we didn't train. We tried different strategies, but we got pure noise as output in the end. This was my work in the last months of this year, but in the end we dropped it because it seems impossible, and also transformers are very hard to train. We couldn't. We will see the results after like 2 to 3 days. The whole training could have gone on for like 2 weeks, and it was impossible. So well, that's why now I'm changing topics. This leads me to the last part of this speech. What is the current state of the art in generative models and what I'm working on right now? In the generative fields, there have always been this trade-off between these 3 points. Either you can have at most 2 of these at the same time. And generative adversarial networks have the advantages of having a fast sampling. You have a single network pass to generate, and the quality can be really good. But as I was mentioning, it lacks diversity, and it's prone to mod collapse. While the most recent denoising models have the capability of covering the whole data space and have high quality at the cost of the speed of the network. But there are some works now improving on top of this. Let me give you a very brief hint of how diffusion models work. I'm not an expert yet on this, but the goal is to starting from some data. The original framework talked about images. The goal is to destroy the image by adding some Gaussian noise and effectively building a Markov chain of noise injection. And the goal of the network is to be able to reverse this process, so of going from pure noise back to the data space. This effectively means that you have a latent space which has the same dimensionality of the original space. Okay, this is the quick and dirty summary of diffusion models. It's adding noise and learning to reverse this. This has some physics basis. Diffusion actually refers to some physics theory about how particles move and how they interact. And on top of this, some more recent research added a different formulation for this, because having this Markov chain, the reverse process can be seen as a stochastic differential equation. And this adds some more mathematical difficulty on top of this and a lot of problems. But as you can see, there are some tricks. This is a pure toy example where we have a mixture of 2 Gaussians. And thanks to this Langevin dynamics, which help the model to sample the whole data space, we can cover the whole space while moving to the more dense regions. Diffusion models started in 2015, but actually they became popular actually only in 2020 when they were rediscovered, and then quickly they became the state of the art for image generation on ImageNet, and this was just in last year, 2021, so 1 year after the rediscover of diffusion models. But the tricks that I'm showing you that that achieved state of the art are mostly engineering, so they are not actually based on any mathematical foundation. And now what we have for diffusion models is this astounding zoo of different applications. We have a pure generation for images, which is better than the best GANs that we have until now. We have, why did the video stop? Okay. We have a video generation, although it is very low resolution for the moment, but we can map also the temporal consistency with diffusion models. And lastly, at the bottom, we have some editing on top of images. And diffusion models are able to find the closest image in the learned space. So we can actually edit images in a very rough way, and the diffusion models will generate the best looking image. And diffusion models are the basis of recent text-to-image models, which I'm sure you saw, like DALL-E, DALL-E 2, ImageN. All of these are based on diffusion models because of their capability of covering the whole data space. In my research at the moment, what I'm trying to do is trying to understand if diffusion models can be paired with NERF, neural radiance fields, which are state-of-the-art for new novel view synthesis. And our goal is to find a possibility to mix the two for having some morph in terms of texture and color without any retraining of NERF. But this is still a very preliminary idea. While on the other hand, what I'm trying to do, and this is in collaboration with Elia, we are trying to work on interactive neural painting, which is a novel field of research where the user is in the loop of the generation of images, and in particular, in our case, of paintings. So the network shall learn how to paint an image given the strokes and in a temporal consistent way, and in the way that a painter will paint it. But we want also the user in the loop, which is able to change how the network is producing the image. And okay, this is all on my side. So feel free to ask any question, any doubts, and thank you again for having me here.
I have a question about the limitation of your work.
Yes.
In anonymization.
Uh-huh.
So you said that the two problems were the time limit
Yes.
for the anonymization that is
Yes.
that must be taken into account your work, and also the supervision of landmarks, right?
These are the two main limitations. Yeah.
But can you do about landmarks also include them during the training procedure, having some, let's say, unsupervised example without landmark supervision, and then use it on test sample without supervision? Is it possible?
Technically, yes. And to be honest, most of the most recent face swapping algorithms do not use any landmark, and they learn an implicit representation of it.
Okay.
But we were not able to get rid of them. So,
Okay. So is still by style we use by for that?
still GANs. They're
GANs.
GANs. Is more or less everyone uses GANs.
Because I know there are conditional by
Yeah.
for which you can provide supervision, but you also work with the supervised set. So they're more about okay, you provide a legal supervision,
Yeah.
but I mean it can be engineered to provide
Yeah.
the lemma supervision. Something seems something that is impossible. I'm also curious about the diffusion models.
Okay.
And I have a very simple question. Because,
Yes.
I'm really amazed about that E2. You were mentioning,
DALL-E 2, yeah.
DALL-E 2.
Yeah,
It's incredible.
Yeah.
And I'm very curious about what are the limitations for these models, because if it is Gaussian noise, okay, it's the simplest noise.
Yes.
But if you go beyond the noise for numbers, are there, any limits?
For the moment, the main limit of systems like DALI-2 is the bias in the dataset, so that the generated images are highly biased towards what the dataset includes. It's not a limitation in terms of generation capability, because that is incredible. And I think that the Gaussian noise is the simplest noise, it's true, but is also the most versatile and the most representative of real world. So
Yes. That you can.
I guess that working with different kind of noise or trying to engineering this will bring some too difficult to analyze if complexity at a minor cost in terms of performances. But this is my gut feeling. But
Yes, also it's a trade-off with time. You can model a lot of things with reduction, or
yeah,
but probably you need more time.
yes.
We have another question about your future research.
Okay.
Is the second one that you presented.
Okay.
In this, can you make some sample of which kind of feed that the user can provide in order to provide to the.
For this, Elia is more expert, but I will answer this. It mostly refers to the deletion and the recreation of paint strokes to match a reference image. So you can tell the network, no, I don't like the way that you painted these strokes, please redo it.
So the network showed me an image proposal, let's say, and then I cannot choose maybe I can say this part of the images is not correct.
What we are trying to achieve at the moment is a class condition generation. So you tell the network which class you would like to paint, and the goal of the network is to model this stroke sequence to match this class. So during this stroke generation, you can stop it, remove some strokes that you don't like, and ask the network to redo it.
Then another one, you mentioned on your slide that you use hybrid learning.
No. I guess this is a misunderstanding of.
I don't remember.
Yeah, I kinda maybe. No. Okay. It's this one hybrid training. In this hybrid training refers to the fact that in face swapping you don't have ground truth, which provides you which is the generated image with the given identity. And to overcome this, we design an hybrid training strategy. Hybrid in the sense that for some iterations of the training, we feed as both condition and source the same image to the network, so we can actually have a ground truth and have a pixel-wise supervision of the generation. Hybrid in this sense.
Question from the people in the chat. If you have any, you can ask.
Do you know any work that try to use also nervous model integration? For what you have seen so far, because it seems that sometimes it can be very useful.
Not that I'm aware of. So
Like imposing some constraints of what you want to generate.
it's not something that I have seen.
Maybe it's too early.
But we can have a chat about this more in depth. What you have in mind? This is. I saw. thank you again. Shall I close the
Yes,
Zoom
yes.
call? So,
Okay, thank you again, Nicola.
thank you. Thank
It was
you.
a great pleasure. And
well.
let's go to the aperitivo, guys, to celebrate. Thank you again.